we can discuss that tomorrow. So I told you that we are in the world of stochastics, and it's really true. Simulation is everywhere today. Everybody has produced data replicates. Some of you also have used simulation to generate stochastic processes, for instance, as Markov chain, even Markov chains or branching processes. And even now, we'll use it for statistical inference, either in the classical or in the Bayesian context. With stochastic EM, we talk Markov chain Monte Carlo in Bayesian. So I will try to make a very brief review of all the steps we need. And the first step we need is to generate IID uniform random variable between 0 and 1. Having this, we can use these ingredients to generate random variable of any arbitrary distribution. And we'll finish by Monte Carlo integration. And as you can see, the basic element in that is a random number. That's why Pierre Lecuyer from Montreal said random numbers are the nuts and bolts of simulation. Everything comes from that. So this is the contents of the course in 3 parts. We first discussed briefly random number generators with some generalities and 2 kinds of generator, linear concurrential, multiple recursive and combined. And I will draw some conclusion, practical conclusions. We'll move on to non-uniform random variable generators, starting with the basic principle, inversion, talking about order transformation, convolution, composition, acceptation, rejection. And we move on to Monte Carlo integration, important sampling, Markov chain Monte Carlo, and metropolis lasting and gift sampling. So that's a long lecture, and apologize in advance to give this in the afternoon, as you already done. There is a long history in random number generation. We started, in fact, with gambling, with cards, dice, balls, lotteries, everything related to Monte Carlo. You know, we are not so far from Monte Carlo, so if you want to practice yourself, you can have a ride there and test the theory. And this led to analogic devices, but with the emergence of computer, we moved very fast by the mid of the last century to arithmetic generators. The most famous one by the mixed square, described in the appendix by 2 famous names, Joseph von Neumann and Metropolis, already there. And in fact, what we'll do, we'll not really generate random numbers, we'll generate what we should call pseudo-random numbers, because they will be produced by a determinist algorithm. So we're not really interested in their nature. Are they really random or not? We are interested in their behavior. Do they behave similarly as truly random numbers? So that's why Joseph von Neumann said himself, anyone who considers arithmetical method of producing random digits is of course in a state of C. So think about that, we are in C for a while in this stochastic era. So, what do we want? What is the property we expect from good random number generator? First, we expect good statistical property. We want IID uniform 0, 1. So we need to test uniformity and independence. And when I mean uniformity and independence, I mean in several dimensions, not only in one dimension. And there are famous serial uniformity tests to do that, especially the diode by Marsaglia and this one you write test U01 by Lecuyer and Sima. We need also to have good mathematical structure. Let's consider, for instance, a sequence of T consecutive numbers. We call T records in the mathematical one. And if you consider this T consecutive number as a coordinate of a point in a T space, for instance, if T equals 3 in a cube, what do you expect? You expect this cube be fully filled by all these numbers. And in fact, it's not the case. With most of the generators we use, there will be some structure in this cube. And so what do we want to avoid? This fixed slice of empty space, as shown, for instance, on this picture. This is for a famous random number generation, RANDU. And now we call 1. And this is the cube, and you see that the numbers are distributed along this plate. You see it's really bad because you have much of space with nothing inside, instead of having the cube completely filled up uniformly with these numbers. So we have to take care of the mathematical structure of the random number generator. What we need also is obviously easy implementation, not to spend 2 days to implement the generator, running fast, you'll see, using little memory and storage, being repeatable. That means that you are able at any time to reproduce the same sequence. Portable, meaning it can work in different soft and hard environments. And last but not least, long period. This will be a crucial point. And Lecuyer, for instance, now recommend period of order 2 power 60 is about 10 to 80. And we'll see how we can meet this requirement. The first two, historically, the first kind of generator we will consider is the linear congruent shock generator. It has been introduced by Lehman in 1951. And it works as follows. You start with a seed, x0. You multiply it by an integer a. You add eventually another integer b. You divide it by n. And you take the rest. And this is your first number. And you repeat. Again, multiply, add, divide, and take the rest. So x0 is the seed, ab are the positive integers, p is the period, the length of the sequence until it repeats identically. And obviously p, due to this modulo, is lower or equal to n. The most used is the so-called multiplicative linear congruential. So it's the same formula except that b equals 0. So just multiply by a, divide by n, and take the rest. And the first kind is with n taken as a power of 2. And the problem with this generator is that its maximum period is just n divided by 4, a quarter of n. So that means that 3/4 of possible numbers are lost. So realize immediately that's not an efficient one. Why they choose this power of 2? It choose it because it doesn't need any division. This result is exactly x written as a big word. And I give you an example. Let's say you want to find the result 28 modulo 2 to the 4, that means 16. So that is the rest of 28 divided by 16, it's 12. Now if you write 28 in a binary basis, this is 1, 1, 1, 0, 0. And if you just take the 4-bit representation, that is you delete this first, you get exactly 12. So that means that you have just to withdraw the overflow. So it's very simple, you don't need anything, you just write the number in this binary notation. Example of such numbers, m to the power 31, the famous roundel, which is horrible, and this one, which is not so horrible, at least in the mind of people, m2 to 59, a13 to 13, p, large period. The problem is this. Until recently, I don't know if I'll change it, but it was the one in the NAG library. Very well known and used everywhere. And as Pierre Lécuyer said, he put a list of all these generators, especially this one. He said they are still popular and you don't have to use them. So avoid this kind of generator. Check if you use NAG, that if this is this generator or not. If it is, change your generator. Now, instead of taking m to the power of 2, in fact what we take is we take m as a prime integer, large prime, and if some mathematical property are met, A, and I want to enter in this property, the period is n minus 1. So particularly all the numbers, because we are generated from 0 to n minus 1, all the numbers are used. And the most famous one has been for n equal to power 31 minus 1. And there is a kind of miracle here, because why this number? First, it was due to some computing constraints. Remember, in the old times, we have 32 bits representation. So if you leave 1 bit for the sign, it remains 31 bits for representation. And with the largest integer you can write with 31 bits is 2 to the power 31 minus 1. So it's the largest number in these old 50s that we are able to write as an integer. But in the same time, this number is also prime, and a very large prime. It's so-called Mersenne number. For the mathematician who are there, they could maybe correct me. It's a prime number having this form, 2 to the power p minus 1, and p is itself a prime. And there is a big competition throughout the world to compute, to find the largest Mersenne number, because it's largely used in cryptography, to break codes. And the last one was discovered in September 2006 by Cooper and Boone. So it's 2 to this power minus 1. I don't tell you how many digits, it's impossible to tell. And the A corresponding to this is 7 to the power 5. So that makes 16,807. There is another choice which is better but not really used. So look here, the power is something like 2 billion. That seems very large, but on account of our needs of simulation, it's not so large now. That's why this generator has to be changed. So the next step is the same principle, but instead of producing the next number from the previous one, you will produce it from a linear combination of the k previous numbers. So you have a vector space with k elements, and you multiply them by different coefficients, a1 to ak, you add all this, you divide by n, and you take the rest. And if you do that now, you can increase a lot your period, because your period now, under appropriate conditions to the polynomial, I will not enter in, your period could be as large as n to the power k minus 1. And such generators are either modulo 2 or modulo large prime. I will restrict myself to the large prime number. And here I gave you an example of such a generator by Deng and Xu in 2003 and Deng 2005. So in that case, what they did is they take a vector space with k elements, but at each step they use only s of them with the same coefficient, a, so as to reduce the amount of computation. So for instance, this dx47,4, it has 47 elements in the vector space, but you use at each step only 4. The -1, -16, -32, -47. With the same coefficient, this one. And the m is 231 minus 1. So it has a reasonable period, 10 to the power of 1,000. So now you have no problem. I gave you also in appendix the dx 1597. This has a period 10 to the power 10,000. So this is a choice you can make, and I'll give you the website address and then you can download this kind of generator. Now another idea is to combine several basic generators so as to get the equivalent of a large modulus single generator. And for instance, as proposed by L'Écuyer 1988 or 1996, you can take two generators with a classical formula, linéaire conjointement, x1, a1, m1, x2, a2, m2. You take the difference divided by m1 and take the rest, and this is equivalent to a large modulus generator. This value for m1, m2, a1 and a2, and this is the so-called round 2 generator. Some of you may be using probably. But it's not the best choice. The best choice for me is this one, with this complicated number. MRG32K3A is combining two MRGs, with each having 3 elements in the vector space, so M1 and 2. For the first generator, A11, A12, and 3. The second, this is the coefficient of the elements of the space. You take the difference, you divide by M1, and you take the rest. And this is equivalent to a large energy with period 2 to the power 191. That means 10 to the power, how much you take the third, 57. So now, having this number, how you generate uniform 1? Usually, what you do, you divide by n. Remember, you are generating 0, 1 up to n minus 1. You divide by n. The problem is doing that, you will have 0. And in many operations, the 0 raise problem. If you talk a lot of 0, you divide by 0. It doesn't like too much. So you have to avoid this 0. Two ways to do that. In den and xu, you add 1/2 and divide by n. So in that case, it varies between 1/2 divided by n minus up to 1 minus 1/2 divided by n. Or you can do as L'Écuyer, divide by n plus 1. So if z is different from 0, you will get up to, you will get from 1 over n plus 1, the start. But if it is 0, you take n. So n divided by n plus 1, that gives you this number. So it's very similar to this, and does not make a big difference on account of the value of n very large if you add 1 and 9. So this is an example in ABIES of the L'Écuyer combined generator, just to show you that to generate 200,000, it took me just 3 seconds. So you have here the mean, 0.5, variance 0.08, it's 1/12, standard deviation, maximum minimum. And it's not terribly complicated, it's just a couple of instructions. But again, you can download it directly from his website. So in conclusion, what you have to do But be careful in using random number generators. Don't do it blindly. Poor and plain bad generators are still popular. And you have to pressure vendors to change that. For instance, to pressure NAG or for instance MATLAB and identify which one you use and its main characteristic, seed and period. And it's not so easy. I'll give you an example. I was unable to know exactly what Winbugs is using as random number generator. I asked several people and they told me it's a lineaire congruential generator, but you see they are all lineaire congruential generators, so it doesn't tell you very much. You have seen several methods, large K-state, vector, then combined generator, the one of L'Écuyer. And there is another one I did not talk about, is modulo 2, is the so-called Mersenne twister by Matsumoto and Nishimura. And this is also a very good one. The problem is to be careful with the seed. This is in fact the one by default in ARM, as far as I know. And now for the future, some people say the future is in quantic random generator, so it is a really true process to generate randomness. The problem with this quantic is that you cannot reproduce a sequence without storage. So if you want to reproduce complete the computation, you have to store all your sequence. It could be a very long sequence. Yes?
Which one is in Fortran? In Fortran?
I don't know. It probably be a lot of software as the lemma, you know, the famous 7 to the power 5 modulo 2 of 31 minus 1. It's still in use in many. So you have to check it. For instance, I don't have, but I can show you the list. For instance, the one in Excel is very poor. It's not recommended. In MATLAB, it was not a good one. So you see, we really use MATLAB as a good generator. And it's amazing because most people don't care. And when I started to get interested in that question, I realized that there would be more problems than we assume. So this is the end. The kind of textbooks about that, they create notes. And also here, the website, you can download Deng, L'Écuyer, and Matsumoto about Mersenne twister. If you go to this site, I have a short note of the MRG with the FPL program. Now we'll move to the second part, adding this uniform number 01, how you generate any kind of distribution. So we'll start with, as usual, we'll start with the basic principle called inversion. And we'll consider random variable continuous one with a cumulative density function f of x. So f of x is between 0 and 1. So what you will do is simply the following. You draw an u from your generator, u01, and you take f minus 1 of u. And this x minus 1 of u is a draw from the distribution of x. And why this? It's very simple. We have to demonstrate that the probability of random variable big X lower or equal to little x is this cumulative density function by definition. This means that x has this distribution. So as f is monotonous, this is equivalent to probability of f of this lower or equal of f of that. But f of f minus 1 is identity. So it's probability of u lower or equal to f of x. But if u is uniform from 0 to 1, this is f of x. So, provided you have a simple expression from a cumulative density function, you can generate a lot of distribution. And we will review a couple of examples. First one is the logistic, for instance. Remember, we use divided logistic with binary data or with growth curves. So f of x is 1 over 1 plus